Vale, bon dia. Ho faré en català, ja que l'Attila està aquí des de fa un any i mig
Sí.
i ja entén molt bé el català. Us presento a l'Attila Çiner, que us farà aquesta xerrada d'exposicions, datació amb isòtops cosmogènics de superfícies que estan exposades. I bé, l'Attila és sedimentòleg, és de la Universitat Tècnica d'Istanbul, de Turquia, i des de fa un any i mig està en una estada aquí a Barcelona, a la Universitat de Barcelona, en el Departament de Geografia, amb el Marc Oliver. I bé, a part de ser professor a la Universitat d'Istanbul, ell és també... You are the president?
Where? Yes. Yes, not anymore.
Ha estat també amb estades com a professor visitant a Orleans, a França, a Holanda també,
Sí.
i bé, i ara aquí a Barcelona. Sense res més, us passo a ell, que us faci la xerrada i després ja comentem el que calgui.
Can you hear me? Yes. Yes. Okay, thank you, Anna, for the introduction and for inviting me. And thank you all for coming to this presentation. And I'm here more or less a little more than 1 year, actually, in the geography department in Barcelona. I work with Marc Oliva. So we are working with him in Antarctica and Greenland projects. But today I'll try to show you some applications of the cosmogenic surface dating that we carried out in Turkey. I concentrate on Turkey, but I'll try to show you not only geomorphology side, but applications to the geology as well. So, okay, let's start. This will be the outline of my talk, and I'll probably many of you know already. This is a new methodology, let's say, since the last 30-40 years. It's gaining more and more importance in the application on the surface dating, cosmogenic surface exposure dating method. I'll just briefly talk about it, and I'll show you some examples where we applied this method, like alluvial funds and landslides or rock falls, and you can calculate the fault slip rates from that. Or fluvial terraces, where you can date the fluvial terrace and then you can calculate the incision rates or uplift rates of the plateau, like Iberia Plateau or Anatolian Plateau for that matter. You can also apply this method to young lava flows. You can date the surface of the lava flow. I used to live in Ankara, in capital city, not too far from Cappadocia. This is probably you heard about it. It's a volcanic landscape with really peculiar landforms. So we try to see how those landforms, how fast those landforms erode away. So I'll talk about that as well. And mainly our applications are actually on glacial deposits, moraines. And I'll finally talk about that as well. So the methodology is based on the cosmic radiation that the Earth receives without any stop, let's say. Any rock that is exposed to cosmic radiation starts to form some new nuclides, like beryllium-10, like chlorine-36, or aluminum-26. So the more it is exposed to the cosmic radiation, the more it accumulates new cosmic elements, the nuclides. So if you know the number of atoms that are produced every year in certain area on the globe, you can then calculate the age of the surface, since when this rock is exposed to this cosmic radiation. Then, of course, you determine the age, but you can also say many things, like in the glacier systems, you can say about the paleoclimate of the system. As you know the age, as you know the moraine is there, so it's not there anymore. So it means that it was colder and how much colder. So you can calculate those things. So I'll show you. So this is actually this is a moraine here where I am on it. It's a really beautiful lateral moraine in the Taurus Mountain in the southern mountains of Turkey. What we do is we just, of course, do a careful geomorphological mapping. We map the systems, and then we start sampling from the topmost part of the moraine here. It should be in its original position, this boulder, because we want to know since when this surface is accumulating those nuclides. So we want to have something solid, so bigger is better here in this case. And on top, from the top surface, we take like 1 kilo of sample. This is limestone, by the way. So for limestone, we use chlorine 36 because from limestone, from calcite, rocks produce chlorine 36 nuclides. So this is the sampling. Of course, we don't want to sample something like here. For example, this block is no good because it could have been here for 5,000 years and then fell. So you date another surface. So you want to make sure that this is the original depositional surface. So we have a lab in Istanbul. I have my colleague, my ex-student actually, he runs this this lab. It's a preparation lab. We prepare for chlorine 36, but also for beryllium-10, the samples. It's a delicate procedure. Then you send this to AMS, accelerated mass spectrometry, to count the atoms in it, and then you calculate the age. Okay, so let's talk about the applications of this method. One of them is the fault surface dating. You have a beautiful, this is from the southwesternmost part of Turkey. It's a beautiful fault surface, you can see. So what we did is to collect samples every like 20 centimeters or so. And then you can see from on the surface as well that this fault moved several times like this. So you want to know the frequency of this fault occurring. So this is actually work in progress still, but I don't think we will do it again for one simple reason. It's because not only it is kind of difficult, but also it's very expensive. And we did not get the result that we really wanted. So this is a method that is used in the world, but some results are okay, but it's not the best. So, but you can still do it. So you know, if you know the age of the surface, this part, and the other part, it's different. So you know that the fault moved 2 or 3 times, whatever thing. So it is done in Italy. There are some works that was carried out. I don't know if there is any in Spain, but I know in Italy there are several. But still, it's a work in progress. It needs some development. So we are working on it. So I just wanted to show this, and I'll skip, and I'll show you another area where we worked, where Anna was there. I took them actually to the field last year. So this is Ecemiş fault, one of the major fault. Of course, you know the North Anatolian fault. This is the equivalent of San Andreas fault, exactly the same system with the same, excuse me. And I will show you some alluvial funds that we dated that were cut and offset by this fault. So this is, by the way, the fault system, East Anatolian fault system, where we had this tremendous earthquake last year with more than 50,000 casualties. So this is the place. So this one also is an important fault system. So here is the Google Earth image of this. This is a high mountain. It's for 3,700 meters here. And you have all these outwash sediments here that you see here from the glacial fund, and you have here you see the fault, and you can say see well, this is the map of the fault here. Here, Gemish fault. So what we did, we dated the boulders on top of the alluvial fund from here to there. Well, you have another system here. This is a landslide. I'll show you this one. This is another environment, let's say. And we dated those alluvial funds. You have several levels of alluvial funds that develop in different time intervals. So we try to date a couple of them. Here's the field picture. We are looking from the surface. So this is, sorry. Here, this is the fault, cutting here, all the alluvial funds. And you can see the offset of the fault. This is, the river was offset for 168 meters here, for example. Or 35 meters here. You can see the river system coming. And this is another surface that we dated. The first surface is 100,000 years old, more or less. And the other surface, which is a little lower, gives 64,000 years old. So then you can, and we obtain this by doing depth profile. This is not surface dating. It is the contrary. It is the depth profile. You do this to get, you sample several samples, like here. This is with an interval of, like, say, 20 centimeters. And you put this banana plot to see the age distribution, and you get one age, which is 64,000 years. So here you do the contrary of the surface dating. You want to know, like OSL dating, you want to know since when this sediment is buried. So this is what we get. The result is 64,000 years. So this is, we published those things in a couple reviews, and these are the results. It means that, okay, this is the landslide that we dated. I just mentioned that you can see this topography, which is chaotic somehow. This is the landslide that happened. It is around 75,000 years. And this one is around 64. And this is probably an outlier, a boulder that probably turned later. So it's not good. So we just use those two ages. So this is two landslides, actually. One of them is around 80,000 and the other one is around 60,000 years old. So you can see from there another fault system. This is the main strand. This is the main fault. And this is another fault that created the landslide. And we dated this. And there you can calculate the slip rate of the fault, like 1 millimeter per year. We also dated some moraines here that you can see. It's this is a high mountain area, and this is the mountain front here that you see, a mountain front fault. And we have really nice small moraines here that you see here, and it is cut by this fault. The moraine is here, and we sampled from the upper and lower parts of the fault, and with two samples, and they are typical last glacial maximum, 21,000 years old surfaces. And it was cut and offset by like 14 meter or 12 meter in both parts. So you can then calculate the slip rate of this fault because you know the age and you know the distance that cut by the fault. I'm not going to get into details. So these are some conclusions that we get from this whole area. How the fault was, how much offset was carried out by this fault. I'll talk about another landform. This is a rockfall in the Taurus Mountains again. We are here. This is southern Turkey. So this is the Taurus Mountains here. It goes all the way to Iran and to Zagreb. This is the alpine chain. This is mostly ophiolites and carbonates in composition. Here you have a beautiful rock slide here coming from here. You can see from the surface huge boulders here, and there is another small one. So we dated those surfaces as well. And I'll skip those. These are some orthophoto with some boulder concentration and maps and block area concentration. So we try to understand the system. And then we date the rockfall here. And there are some hummocky moraines nearby as well that we dated as well. So we have the ages of those rockfalls. I'll show you in a better picture. So these are the blocks, huge blocks. So the two systems are very closely dated. One of them is 4,500 years old, and the other one is around 3,700 years old. So you had two major landslides in mid-Holocene. So, and if you put this in the context of climate of that time, well, with some other proxy data from the Taurus Mountains, these are our ages, and these are some other proxies coming from rock avalanches or rock slides as well. So this is the wet and dry phases we encounter. So we try to fit in which of the wet or dry phase that falls. It's not an easy thing to do, but sometimes it works. Here in this case, we know that this event, the younger event, it was a wetter time, and the older one came in a dry season. Another application is still from Cappadocia. This is also a Kızılırmak River. This is the biggest river in the country. It's around, I think, 1,500 kilometers or so. So it goes all the way to the Black Sea. Here you can see the fluvial, the river itself, and here you have one of the terraces. You have several terraces. So what we do is we want to understand the plateau uplift rate. So this is the Anatolian Plateau, by the way. This is Ankara, and Cappadocia is here, and somewhere here. It's very typical. It's comparable to Iberian Plateau. It's a well-defined plateau. High mountains on the north, high mountains in the south, and dry and lowland in the center. So it's around 1 kilometer high. So you can see a section through here. This is Mediterranean, and this is the Black Sea. So you have this nice deposits here. So here is a village, Avanos, where you have the fluvial system, and you have several layers of fluvial terraces. Here is one. Here is another one. There are one more here. You can't see, but so what we did is to sample from the surface some sediments so that we can date them. We also sampled, we did some burial dating, the one that I explained in other systems. So this is the sediments on top. This sediment was buried. We sampled from here to understand since when this sediment is buried. So you can calculate the age. Of course, for this, you need to have two nuclides, aluminum and beryllium, and each of them, their decay rate is almost double compared to each other. So you can then calculate the age. We also have a lot of basalt flows there. This is one of the airports, by the way. It's a very dry land. You can tell, this is really very continental. It's around 500 millimeter per year of precipitation. So we have several basalt layers. So you can see one inverted valley here. This is a basalt layer which dates to 2 million years. And this basalt layer is 400,000. So we have several fluvial terraces in between. So we use those dates as well. Here you go. This is the image of the terraces. So we map all the terraces, and there's a fault system here. And put those terraces, the reds are the basalt dates, and those ones are the terrace ages. I won't keep you too much with that in detail, but the ones that we dated, so you plot on the chart the age and elevation above present river chart, then you can, the best fit gives you the incision rate of the fluvial system. In other words, this is your plateau uplift rate. So what we get here is something around, if I'm not mistaken, 50 millimeter per million year, 50 meter per million year. It's pretty low because in the south, we have also work in the south, in the Taurus mountain range. It is like 10 times more than that. It's much faster. The south, because of the subduction under the Cyprus arc, is uplifting much faster than the central part. Okay, I'll pass to another application. This is dating the lava flows. This is RGS mountain in Cappadocia, nearby Cappadocia, a beautiful mountain. We dated several moraines here. I'll show you in a minute. But what I'll show you is you have many monogenic centers around. You can see one here, one there. There are 60 of them, actually. So we dated 3 or 4 of them. Here is the map. Okay, 3 of them. So those are lava flows, Kar, Per, and Dik. Beautiful lava flow, very fresh looking. So you can see the lava flow, and we dated, those are sample sites here. And the ages are pretty nice, actually. It's around between 8 to 10,000 years, the lava flows. All of them, all those different lava flows. So it means that you had a major activity 9 to 10,000 years ago in this area. We were also lucky, we found some charcoal in the ignimbrite layers that came out from this lava flow, or before, just before. So we dated this, of course, and it gives exactly the same age. It's 9,700,000 years. So this is, we did in a couple other places, this lava dating. Also, this is also a somewhat problematic issue because you date with chlorine-36, but you also have chlorine-36 coming from the magma. So you have to discriminate between the chlorine-36 autogenic one that comes from magma compared to the one that it is produced on the surface. So it's kind of problematic issue, but people are working on it, and it will get better and better, I think. But it's still doable. You can date the surface. Here it is. The results are here, 9,500 and things like that. It's not too far from each other. Okay, this is the famous Cappadocian landscape. We call them fairy chimneys. These are these are all ignimbrite, ignimbritic explosion volcanics. It starts 11 million years ago, and you still have some activity. Well, it's not active, but we know that we have some Holocene lavas and even tuff produced in the area. So you have different layers with different composition and therefore different erosion rates. So we want to know how fast this landscape is eroding. So you can do that with the cosmogenic dating. So one of the area, this is of course a very touristic area with lots of very popular balloon flights and underground cities. It's a soft material. People, first Christians especially, they came and carved in those rocks in the area. So beautiful valleys with fairy chimney, different styles of fairy chimneys. And you can tell from here, this one is different than this one. And in between you have another layer. So, and they erode differentially. There you go. And once the head is gone, the erosion is faster, but how much faster? We want to quantify this. So this is what we did. So the head is gone. You can see the erosion is much faster. You can really feel this on the field, but we want to know the numbers. So what we did, we collected in several stages, like the plateau stage. This is how they form, by the way. This was a one layer, and because ignimbrite it explodes around 300-400 degrees Celsius, it settles and it starts to cool, and you start developing cooling fractures, like here. Those are cooling fractures. And of course, rain and wind erosion will help shape those, what we call fairy chimneys. And the ones that are forming here and the old ones with no head are doomed to disappear completely, of course, one day. So this is what we did. We sampled all this line to see how fast they are eroding. And here are the results. The method is somewhat complicated. I don't understand myself either. So I just use it, the mathematics of it. But you can see, for example, on the plateau, the erosion rate is 0.6 centimeter per 1,000 year. This is the plateau erosion rate. You can calculate the age as well, but you calculate the erosion. What is interesting for us in this case is the erosion rate. And here, for example, is 3.5 centimeter per 1,000 year. Once you start the pre-chimney transition stage from the plateau, which is 0.5 to 3.5. It's almost 6-7 times faster. When you pass to this chimney stage, it's around 3.5 again. It doesn't change much. This is the age. But once the cap is gone, the erosion is much, much faster. It's 28 centimeter per 1,000 year. So it's like there is almost 10-fold increase in erosion rate when the hard ignimbrite body is gone. The softer one erodes very fast. So this is the conclusion with the ages. Erosion rate increases, and of course, apparent age decreases in this case, because when you erode faster, all the nuclides concentrated, they are gone, so the age becomes younger. Okay, for the last part, I will talk about the glacial deposits. This is what we do mainly, actually. We are more specialized on that. And we dated many mountains in the south and in other parts as well, but I'll just give you a couple samples from here, not to take too much of your time. This is Ala Dağlar, the mountain that I showed you with the alluvial fans. It's a beautiful mountain landscape, and and you have a nice plateau there, and it's just a very touristic site as well. You do like 2-3 days of walking, and you cross to the other side. We did this a couple of times. It's really beautiful. So we mapped and dated the moraines. of course, moraine, as you know, this is the deposit by glacier. It was here, the glacier, but now it's here. It means that the climate changed. So it's more warmer today. So we know that. So if you can date this, you can, and you can, with some modeling, you can understand how the temperature or precipitation change in the time with the equilibrium line altitude. So I'll start with a couple mountains. This is one of the southwesternmost mountains, Akdağ. This is the Mediterranean here. I'll show you 3 valleys here. A beautiful moraine, really textbook moraine. Here you can see, you can feel the glacier even. It's just gone, but the moraine is there. So we dated them. It's 21,000. It's very, very nicely LGM, last glacial maximum. This is the time when the glaciers were in the last cycle were at their maximum. Often, not always. In the southern hemisphere, for example, this is not the case, but here in the northern hemisphere, it's 21,000. It's kind of norm. For example, we dated another moraine here to 39,000. It's before the last glacial maximum. It's older, but the last glacial maximum moraine was more severe. So the climate was colder in that time because it came even much more down. So if the glacier goes down, it means that the climate, of course, is colder than that time. So this is the late glacial, 15,000. So this is the chronology of this glacial valley. And we compare this with the Greenland ice cores, and you can come up with some paleoclimatic interpretation. What we do is we model the glacial, we use one-dimensional, now we use even two-dimensional physical glacial flow models. And in this case, for example, if you put in the model the surface topography, modern climates, modern temperatures and precipitations, and the model will run for you, and the output will be the thickness and the length of the glacier, in other words, the volume of the glacier, and you compare this with your field observations, and then you have, you can say something about the paleoclimate. In this case, for example, the LGM glacier was almost 6 kilometers long, and you needed around between 8 to 11 degree temperature, Celsius degree temperature drop if you assume similar precipitation conditions as today. If you increase the precipitation, you can find here, you need less temperature decreases. If you are in drier conditions, you need colder conditions. So this is the model prediction. Another area we dated is it's a nice Piedmont glacier here. You had an ice cap here, and that came down and deposited all these moraines here. Here are the moraine pictures. It's a beautiful area as well here. And you have, these are Hamoki moraines. These are dead-eyed features, mostly, when the glacier is covered with boulders, and the ice is detached, and once it melts, they form some hummocks, some small hills. That's why they call them Hamoki moraine here. And here's a lateral moraine, for example, here. And those area is the Hamoki moraine. And you can see a really nice section of a moraine, unsorted, unstratified till. This is the definition of the moraine. And from the surface, we date this to 18,000 years. And you can see soil formation in 18,000 years. So it's a good indication that the soil forms sometimes pretty fast, especially in limestone bedrock. These are the ages we have there, Younger Dryas, Late Glacial. I'll skip this. This is the mountain chronology. And I'll show you the moraines that we dated on the Erciyes volcano. Here's a nice, this is a ski valley, by the way. People are ski here on top of the moraines and rock glaciers. It's a beautiful mountain again. And we dated some moraines on the other side, on the northern side. This is the moraine here. It's again 19,000. It's typical last glacial maximum moraine, and the outwash plain is 2,500 years old. What is good about here is that we still have a small glacier that is surveyed since 100 years, so we can calculate the speed of melting. In other words, we measured this in 2001, for example. It was here, probably today is somewhere here, but it was 100 years ago, it was even much, much lower. So you can calculate the melting rate of this glacier. To form those LGM glaciers, here again, if you run the model, you can run for any time interval you want. With the same precipitation as today, you need to have like 8 to 9 degrees Celsius of temperature drop to form those glaciers in those times. So in other words, in Anatolia, especially in the south and in the central part, because in the north is a different system from the Black Sea, but there in the temperatures, paleo temperatures were between 8 to 10 degrees Celsius lower than today, 21,000 years ago, which is more or less confirmed in the Alps. In the Pyrenees, it's a little different. It's a little earlier for different reasons, but in Anatolia, this was the case. We compared this with some proxy data. You can take lake isotopes or speleothem data here, and they fit pretty well. I won't go into detail. And lastly, I'll show you the Aladağlar system, where we dated several moraines. We recently published one paper there. This is the top of it's from a plain, the top where you had an ice cap, and this is where we had this alluvial funds that I showed you. What we did there is it's a huge mountain. This is one of the deepest karst system in the world. This is huge caves, and we dated most of the moraines there, but I will just show you this system here, a huge glacier, Hacer Valley, on the eastern looking side, with beautiful moraines. Here you go. This is from the plateau, take from 3,200. And here is 1,000 meter almost in this down there. So there was a huge, like 17-kilometer long glacier that came down here and start retreating. So we dated 7 different recessional moraines here. Here I'll show you the results. Okay, this is one of the moraines, and this is moraine G is around 1,000 meter, 1,100 meter. And the A is around 3,000 meter. And you can see the ages. It starts from 14,000, and this one is 13, 12, 50. So as the glacier retreats, the age also decreases. It's very nice data set that we published in geology 10 years ago almost. So you can do the temperature and precipitation drop here. For this part, you need 4 degrees Celsius of cooling for this early Holocene or Younger Dryas even moraine. What was interesting here is that during the deglaciation occurred in 2 phases. During the first phase, the glacier was retreating at an average rate of 400 meters per century. But later in the second phase, it became much, much faster. It started to melt at 1,700 meters per 100 years, implying a warming rate of 1.5 degrees Celsius per century, which is even more than the last century's warming rate. This means that, this was our conclusion, this rate exceeds the global warming trend of the 20th century, showing that natural causes can lead to fast and large climate changes, even before the humans. Nature can do a very fast climate change. I'm not minimizing the human impact here, don't misunderstand me, but nature also can do that very fast. The magnitude and rate of climate changes observed in the past century are not unprecedented. So long ago, we also had some very fast warming of temperatures. So we put here all the proxy data. I'm just showing you, I won't go into detail, lots of data from surrounding mountains to understand how the glacial termination, the glacial cycle was represented in this Aladalar part. And finally, this is another mountain just 20 kilometers south. I'll show you this because we did a different modeling here, and I'll finish with that. This is a Karanfil. This is a mountain. Those are cirque areas and the moraines. This is a beautiful, you can see moraine and moraine. We have several, 4 moraine system there. We sampled those boulders, and with the drone, you can see beautiful moraine with boulders and recessional moraines. And here are the ages of different systems. It's around 2018, so it's last glacial maximum, except this one. This is late glacial, but this is, it was looking north facing, so it's, the glacier stayed a little longer there. So these are the results. But what we did here is we used a new model, which is called parallel ice sheet model. This is developed for ice sheets, actually, for Greenland or for Antarctica. But we applied this in valley glaciers as well. So what you do here is one means this today's precipitation values, and this one is 25 drier and 25% wetter conditions. And then you start, those lines are the moraine limits. Then you start running the model and see the best fit to this case. For example, 9-degree drop with today's precipitations, or something like this one, 8.5 with a little more precipitation will fit better. So you kind of play around to see what is your best fit to this thing. Another good thing is that sometimes you work in very tree-covered areas where you don't see the moraine. If you run the model here and then go to the field, the model will tell you should have some moraines here. So you can check this. And we did this in the Pyrenees, in Kadi Mountains recently. So we collected some samples not too far from here, where it was covered by moraine, but the model says it should be some moraine there. So we went there, and there were some moraines. So it's a pretty cool thing to do. And in the best fit model, it's again the same thing. Like you need like 8 degrees Celsius drop in today's conditions. This is all Taurus Mountain. I'll skip that. This is the conclusions for the paleoclimate of the country. LGM is, as in many European parts, is very similar 21,000 years ago. Late glacial, younger Dryas, late Holocene. So glaciers are melting. That's what we can say for sure. And we have still some glaciers, but not for long, unfortunately. Probably in a couple decades, they will be all gone. I will finish with this publicity, I will say. We are organizing since 4 years a conference called Mediterranean Geoscience Union that we started in Istanbul. we did in Marrakesh, but this year, as I'm here, we are organizing in Barcelona. So this will be in sometime in November. So there are already 500 abstracts. So we are very happy. We will organize this in November, so you are welcome. I'm also editor-in-chief of this Springer Review. So if you have, we are concentrated on the Mediterranean environments mostly. And if you are thinking of publishing something in our journal, I can promise you a very fast and fair review, let's say. And with that, I thank you very much for your attention. These are my colleagues, Akif and Cengiz, by the way, with whom I work. And this is our team. Thank you. Any questions? Go ahead.
Thank you, Attila, for this nice presentation and clear.
Thank you.
I'm sure that there will be quite a lot of questions. So if you want.
Yeah. Thanks, Attila, for the talk. It has been really, really nice.
Thank you.
Just a question. Being in a highly tectonic environment as Turkey is located, how you the tectonics should are a key role in the erosions apart from the glacials. I mean, how do you see the relationship between the tectonics and the glaciers? Because you said one of the conclusions you showed before is that the erosion rate now it's much higher than there was one slide talking about the if you go a little bit.
The slide on the glacier, you mean?
Yeah, and this ones you are talking here. You are talking about the previous one. This one.
Oh, sorry.
You're saying that the natural causes can lead to fast and large climatic changes, right? But here you have the tectonics playing a key role in Turkey because you have a large tectonic environment. How do you
You mean
distinguish between the tectonic and the climate?
But I mean, if you are talking about the uplift, I mean, due to the tectonic, it's negligible, I would say, because, for example, in this mountain range, in this Aladağlar where I showed you, in 20,000 years, the mountain fault uplifted, I mean, for only 14 meters. The uplift of the plateau is only 14 years in 20,000 years.
Yeah.
And even much less if you look to the fluvial incision rates, it's 50 meters in 1 million years. So the plateau is uplifting 50 meters in 1 million years. In the south, as I said, it's 500 meters. It's very fast uplifting because of the subduction and they think there's a plume break off. So it's very, very fast uplifting. But for the glaciers, not erosion, but the tectonics doesn't.
So you have the tectonics in one side and the glaciers in another side?
No, you can have tectonics anywhere you want. Of course, we have tectonic places, but it does not affect your glacial environment because we are talking only 20,000 years old glaciers here. They are comparatively, they are very young. So the tectonic does not affect very much this.
Okay, thanks.
More questions? No? I have one.
Yeah, go ahead.
When you did the datation of the fault plane,
yes,
you are assuming that the fault moves when it arrives to the surface because you are dating. I mean, when I see a fault, I always think that this fault was somewhere.
Yes, I understand. Yes, of course, we want to. Yeah, but the thing is, I mean, if you see the silicon, the mirror of the fault, so you can tell from the erosion characteristic that this was, of course, on the surface. I understand what your point. I mean, it might be under, but that's the point actually. It is under here, and it comes, and now you have the cosmic radiation on top. This is the surface that you are dating. But it does. I also understand what you mean. It could have been covered and then cleaned again later. But the time interval that we are talking is like couple thousand years, couple 10,000 years. So the erosion is not that fast, especially for a huge, like couple 100-meter long fault mirror. You understand what I understand your point, but yeah, of course, this is your field observation, and you want to make sure that you are dating something that was already there, but it starts moving like this. It should be a normal fault. You don't want to date a strike slip fault.
And how old can you go?
Well, it depends on with the limestone, the chlorine 36 is the midlife is 300,000 years. So you can go all the way to 1 million years old, but this is the very maximum limit. Yeah.
More questions?
Hi, thank you so much for the presentation. Maybe it's a very dumb question, because I'm not an expert on. Would it be possible to integrate, or how would you compare data obtained from your cosmogenic analysis with OSL dating? Is something that you normally do, or you?
You mean compare the OSL and cosmogenics? Yes, we did this in several places, actually. Of course, for OSL, you need quartz grains often. And in limestone area, you cannot use this, but we did in the Black Sea or in other parts of Turkey or globe. For glaciers, OSL dating is not a very reliable dating. This is our experience. But for other fluvial systems, for example, provided that you have fine quartz, they are excellent. We have a couple papers on the Black Sea part where we combined OSL with cosmogenics, and they perfectly fit each other. For fluvial terraces, though. Fluvial and marine terraces. Yeah.
Okay, thank you.
Any more questions?
Yeah, thank you for the presentation also. And going back to this slide, I think.
This one?
Yeah, this one. Well, he pointed, okay, maybe tectonics is negligible, but this model is very dependent on the precipitation rate. Is the weathering involving in the calculation of the
Yes.
Yeah.
It's a good question. It's of course we take into account the weathering of the boulder, because the cosmic radiation produces nuclides. If you have a very fast erosion, those nuclides will go away. So your calculation will be wrong. I mean, you will have younger ages. So especially, we have a very recent publication on this. We try to understand in the Dinarids and in the Taurus Mountains how fast the limestone bedrock is eroding.
Yeah, exactly.
Yes, we use an erosion factor for each site, depending on the precipitation that we know of. For example, in the Dinarids, where we worked a lot, you have huge precipitations in Croatia and things like that. It's around 2,000 millimeter per year. So you need to take more erosion into the calculation. You do many erosion correction, error correction to your age. For example, if you are in a huge valley like this, your cosmic radiation is blocked by the mountain. So you need to take into account in your age calculation this as well. Of course, there are many details on that. I didn't mention here, but of course, yes, you do take into account. In the Taurus Mountains, we take 5 to 7 millimeter per 1,000 year of erosion. This affects, if you were to take only 0 millimeter erosion, this will change your result by 4 or 5%. This is the amount. If you take the erosion corrected age, it will be 5%.
So it's not so much, really.
It's not so much, but it is still important. So you need to take into account.
How about the precipitation rate around the past 20 million? Because this also will affect this number. I mean,
yes, of course. Well, of course, we don't know the precipitation rate. You can only use proxy data from the lake sediments, paleothems, and things like that. And we combine all these things and decide that, okay, we will use this amount of erosion for this boulder, for example.
Thank you.
Yes, thanks.
Questions?
No, thank you. And thinking about the possible uses of cosmogenic in paleoseismology, is it possible to use it inside a trench, or you need a wide and very exposed place?
Inside of?
A trench, a paleoseismic trench.
No, no. You can, well, the answer is yes and no. So you theoretically, you need exposure to cosmic radiation. So in a paleo trench, you don't have that. It's a covered surface. Then you make a trench yourself, artificial trench. So it's not good for this unless you do this with an alluvial fund that I showed you. We did a trench there, but then we do the burial dating, not the surface dating, but what is called burial. It's exactly the same principle as OSL dating. But of course, you need to see your fault there and the offset and the age of your sediment. But you are not dating the sediment. You are dating the time of deposition of that sediment, of course. Yes. Yes, you can do that. But of course, people will often do with carbon-14, of course. But then your age interval is 40,000. So, yeah.
More questions? No? Well, thanks, Attila.
Yeah, thank you for listening. Okay.
Thanks to everybody.